lesson 62, Newton's second and third law. We will be able to explain Newton's second law and third law if we get time. I'm not sure, depends how long we get. What I'm going to do is I'm going to give you guys, going to go through Newton's second law, then I'm going to give you guys 20 minutes to work on some of the questions, and then I'm going to go through Newton's third law. Now, Newton's second law is unique because it's the first one that's got some actual, it's the first of Newton's laws that actually has calculations in it, rather than Newton's first law, which was just a quick refresher of Newton's first law, was an object in motion will, an object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an unbalanced force. In other words, a net force. We said that you can also say, yeah, if you've got zero net force, you won't move because there are no unbalanced forces. You won't move or you keep moving at the same speed. It's only when you experience a net force that you'll accelerate, which is sort of, I think it was like net force causing acceleration. This one down the bottom here, but all of these are different ways to refer to Newton's first law. What we did was we went through a thought experiment. It's like, okay, fine. Like objects want to stay at rest. That makes sense because if you move something, it eventually stops moving. But how did they come up with this idea that an object that's moving will want to keep moving? We went through Galileo's thought experiment. Then we talked about inertia. Was inertia? Tendency not to move. I could refer to this as well as my couch potato analogy. It's really hard to get someone that's comfortable in a seat to move. The more comfortable you are, the more inertia you have because you're less likely to want to move. And so we talked about inertia. We showed you this crashed truck and said, well, again, this is an example of inertia. It's like the rock is very, very heavy, so it's very, very difficult to stop its motion. It wants to keep moving forward at the same speed. So when we talk about Newton's first law, it's a law about inertia. It's a law about how hard is it to, you know, how it's not, inertia sort of says it's difficult to change something's velocity. Like it just doesn't naturally happen. You have to do something to it to change its velocity. We talked about the train example, person on a train and the person moving at the same speed forward. Train stops, person's going to keep moving at that same speed forward because an object in motion will stay in motion. It will keep its inertia unless something stops it. So that person will probably grab onto a pole or they'll fall over and they'll fall forward as well. That's important to remember. This is why we have seat belts. And then I gave you guys the rest of the time to work on 10.3. Now, what I do want to show you guys, actually, before I go too deep into this, is that I also uploaded, just as something in case you're interested, this video here. It's an interesting, this is the one that I was talking to you guys about. It was the one about the balloon that goes backwards. And he actually explains why. He uses a bubble in a bottle of water, and how even though the bubble, if you push the water bottle forwards, the bubble moves to the back because all the water moves to the front. The water is like the girl falling over on the train. Definitely worth a watch. It will probably help you understand Newton's first law a bit, and it gives you some information about like why things. It's interesting because it looks at why things might not always follow the laws that you might be familiar with. They actually are. They're just exhibiting it's like two or more laws crossed together. In fact, that's what I think makes Newton's laws a bit more complex. Is not each individual law. As I said, I'm going to go through each law. It's going to take me about, as I said, 3 periods to go through the first, second, and third law. That's not what's difficult about it. The first, second, and third law, they're pretty easy to learn. What's difficult is when all 3 of those laws start to interact. When you start getting the situations like, oh, well, this is a case of the Newton's third law with Newton's first law also being implied. That's when it starts to become a bit challenging. All right, let's go back to today's lesson. Let's tackle the second law. Now, these slides I've ripped out of just old PowerPoint, so don't expect anything necessarily flashy. I just wanted to quickly get through it. Then I also wanted to grab a look at the textbook and see how the textbook approaches this topic as well. So a lot of you guys have seen this question before, but those of you that haven't, I want you guys to answer this question in the chat. A spring is designed to provide the same amount of push on a ball to a ball, so the same amount of force to a ball. One ball is made of plastic. The other ball, the same size as the first ball, but is made out of steel. Which ball will go further and why? Can I get you guys to answer that? You know what I want most people, I want to try and get everyone to put an answer into chat. Which ball will go further and why? If you guys have done this question before because you've been in my engineering maths class, great. You should be able to get this 100% correct. So, which ball should go further and why? In chat. Or out loud if you really want. Plastic. Good job for the why. Same with needs less force. Okay, cool. Thank you, Kelvin. Someone else. Plastic or steel? I want to get a couple of people. I want to get like at least, half the people to answer something here. Come on. Tam, Vince, Tien, Vaughn, Leon, Morrison, Phoenix. Which ball will go further and why? Privately, someone said the plastic ball has a greater acceleration. Okay. Talking about acceleration instead of force. What else can we got? Someone else. Privately, someone said plastic ball has less mass. Okay, yep. Plastic ball does have less mass. That is correct. And that's another reason why. Let's get two more. I want two more answers. So properties. Kelvin, I've already got an answer from you. But yeah, Arn, where are you? Arvin, give me an answer. Daniel, I'm looking for two more answers and then I'm going to move on. Plastic has less inertia. That was written by someone, probably. That's true because it's got less mass. It has less inertia. So therefore, it will speed up easier. And let's go for one more. Come on, one more. I'm looking at Anthony, I'm looking at Brendan, I'm looking at Jason. Plastic is lighter. Yeah, okay. Someone said that. Steel heavier means it's harder to stop, thus travel further. Ooh, Alicia's giving an alternative answer. So, yeah, most of you guys are pretty much correct. The plastic ball is the ball that goes further. And the reason why the plastic ball goes further is actually pretty important. Plastic ball goes further because, yeah, it has a lower inertia. That means it's easier to change its velocity. So it's easier to speed it up and make it go faster at the start. The steel ball will move, and the other person is correct. It will be harder to stop it, but it won't move as fast because it needs more. It's got a higher inertia, so you need to put more energy and more effort to make it go faster. Now the question might be like, okay, well, if this plastic ball moves faster, then why does it move further? Well, the faster it moves, the longer it'll take to slow it down, compared to a steel ball, which will be the same thing. It'll probably depend on friction as well, or air resistance, depending on how you fire the object. So what we end up with is this idea of the second law of motion. Now, what is the second law of motion? When an object experiences an unbalanced force, so when an object experiences a net force, it will accelerate proportional to its mass. The force is equal to the mass times acceleration. This also gives us evidence as to why force as a vector, because force is dependent on acceleration, and acceleration we know is a vector. So therefore force must be a vector. So this is Newton's second law. There are probably other ways to write Newton's second law, but this is just the simplest way. F equals ma. The force is proportional to the mass times acceleration. We've already seen this formula before because we saw F equals mg. For we saw that g was 9.8, but that's just the gravitational acceleration. This is a general form. Now you guys should hopefully, guys and girls should be all right with understanding this as a basic concept. If you've got a heavy object, you need to apply a greater force to give it the same acceleration. If you're in a race with a billy cart, which is just a little cart that kids push around, if you don't know, and you've got a really, really heavy billy cart because your dad thought it would be a good idea to make the chassis out of steel instead of out of wood like all the other dads made their billy carts out of. Not that that relates to anything. It's going to be really hard to move it. You're going to need a lot more force to get the same acceleration compared to the other kids that are pushing wooden billy carts. They're going to need a lot less force to move their billy cart the same speed, and so that's why they win the billy cart race. And you've got a big billy cart that doesn't go anywhere because it's too heavy. But yeah, that's what Newton's second law is. The greater the force, the greater you can get a great acceleration as long as you've got a low amount of mass. Now, oops, sorry. Okay, so this also ties together as well with Newton's with the idea of objects falling. So an object that falls, actually I'm not going to do that because I'm going to get it wrong. I have a tendency to get these things wrong. I don't want to get it wrong and get you guys more confused. I will talk about that later on if I figure out how to do it correctly. So that's Newton's second law. Let's start using it. Okay, let's do two quick examples. The first example is, we'll do two quick examples, and then what we'll do, and then I'll wrap that up for a little while. So a hammer has a mass of 1.5 kilos. The acceleration needed, what acceleration is needed to ensure it hits a nail with 40 newtons worth of force? Well, how do you do this? F equals ma. Guess what? We need to rearrange this because we want to get an acceleration. So our force divided by our mass gives an acceleration. In this case, our force is that we want to get is 40 newtons. We're trying to move a 1.5 kilogram hammer. So 40 divided by 1.5 is going to be 27. I don't know. Is it 60? No. That's times 1.5. 40 divided by 1.5 gives us, about 27. 27 meters per second squared down. Straight away, someone will ask, do I need to write down? Yes, because it's an acceleration. Unless it talks about what magnitude or what size acceleration, and because there's a nail, I'm just going to write down. It's better to write a direction than no direction sometimes. Because at least if you write a direction, you can be like, oh, well, at least they knew they had to add a direction. So that's the first one, rearranging F equals ma. You guys will see a lot of those. They're pretty stock standard, easy to do, but give it a go. The next one here is a 200-gram glass is pushed off a 1.2 meter high table and takes 0.5 seconds to hit the ground. What force will it hit the ground with? Now this is a little bit cheating. It's actually a bit silly because we already know the acceleration by gravity, so we could just figure this out. But let's pretend that we don't, and I'm going to have to change this for next time so that people don't use that shortcut. So what we're going to do is we know that it's a 1.2 meter high table. It takes this much time. Let's say that we wanted to work out what force it hit the ground with. Maybe this glass isn't on Earth, so we've got to work out F equals ma. Now we know that the mass is 0.2 kilograms. Now this is a trick that you guys probably don't know yet, so just so you do know, you always have to use kilograms. So you have to convert this to kilograms first. Okay, that will be something that you guys will learn probably the hard way when you get the answers wrong on tests and questions. But yeah, I thought I'd throw that in there just so that you guys were clear that you could see where that comes from. Now the glass is pushed off a 1.2 meter high table. We don't have, the problem is that we don't have acceleration. We don't know what the acceleration is. So to calculate the acceleration, we're going to use the facts that are given here. We've got S, which is 1.2. We've got 0.5 seconds, so we've got T. And then we've got U, because our initial velocity, what we've pushed the glass off with. We're not going to push it down. We're not going to hit the glass downwards. So therefore, we're going to assume that our initial velocity is 0. And we want to calculate A. So S, T, U, and A, we're going to use the formula S equals UT plus half AT. And now I'm going to go through this quickly because because I can't draw properly. UT is going to cancel because I've got that 0 there. You will see that happen a lot because you've got either U is 0 or V is 0. You can cancel it at that term. So we end up with S 2S divided by T squared equals A. In this case, it's going to be A equals, and I reckon if I'm smart, I probably tried to make this close to 9.8, but we'll see. 2 times a 1.2 meter high table divided by 0.5 squared, 9.6. Look at that. Did a pretty good job there. So that's 9.6. So maybe this is like, I don't know, maybe this is high altitude. Maybe this is actually, this glass happens to be on a plane circling the Earth. So now we've got that. We can go 2 times 9.6. 0.2 times 9.6, which is going to give you the answer of 0.2 times 9.6 is going to give you 1.92 newtons. So, whoopsies, 1.92 newtons. Now you could say down or you could say towards the ground, doesn't matter. But yeah, those are 2 examples of how to do this. And now what I'm going to do, I'm going to take a bit of a, wait, before I do that, are there any questions or queries or issues that you guys have with this? Have I done it too quickly? Okay, so now what I'm going to do is I'm going to jump over to here. So this is where we were last time. Here's 10.3. La, 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 la. 10.4. Now 10.4 is the same idea here. And it talks about how we measure force and mass. And they figured out that this is the formula. The net force is equal to the mass times acceleration. And as you guys can see here, again, both of these are vector quantities because they've both got these vectors above them. So that's how we know. It then talks about determine Newton's second law allows you to determine the net force of an object, determine the mass of an object, or predict the, yeah. So this is, by the way, you can use this to figure out the mass of an object. So a lot of people turn around, they always say, how the heck do you measure the mass of the Earth when you don't have a scale large enough to put underneath the Earth? It's like, well, if you know the amount of force that the Earth is experiencing because of gravity, like by being pulled by the sun, and you know how quickly that Earth is moving towards the sun, you can use that to figure out the mass of the Earth. So that's sort of how you can calculate masses when you don't know what they are. So here is an example, just like the one that we just did. This is applying it in real life. Now, yeah, as I said, a lot of these questions are going to involve air resistance, but we're going to ignore it. So just ignore air resistance. So then we've got this example here. An 80 kilogram bungee jumper is 24 meters above the surface of the water. What is the acceleration at that instant? So this is going to have to be another calculate the acceleration questions. And then this one looks like it's pretty much the same. Oh, okay, so this is balancing the forces first. And then, so you've got to figure out, okay, so the net force is, you know, and that's one of the other ones as well. This will be really good for helping you guys calculate net forces. And yeah, what's this one here? Ooh, that one looks hard. The following velocity versus time graph describes the motion of a 45 kilogram girl on roller skates as she rolls along the horizontal concrete for 6 seconds before crossing onto rough gravel for the remaining 4 seconds. So she's going at she's slowing down her velocity, but then she hits the gravel and then she quickly slows down her velocity. So she eventually stops. She reaches 0 velocity in 10 seconds. What is the magnitude of the net force of the girl? So if you have two velocities that are different, so hold on, this is a velocity here. So what is the magnitude of the force on the girl on the concrete part? So if you measure from here to here, and get the acceleration because of the gradient of velocity time graph is acceleration, you know she's 45 kilos, you can get the friction. Then you got this complicated thing here, but you guys can figure that out. You guys are smart. Okay, so what I would like you to do, okay, and I'm always going to get, this is what I was going to talk to you guys about, but I was worried I was going to get it wrong. So I'm going to look that up. But yeah, I'm going to look that up before I do that. What I'm going to do is we've got 10.4. There are a lot of questions. There are 10 questions in 10.4. What I'm going to do with you guys now is this. We're going to spend the next 25 minutes, so that's till 12 o'clock, working on 10.4, just doing some of the questions there. And then at 12 o'clock, we're going to start talking about Newton's third law, okay? So what I'm going to ask you guys to do now is, and I'm actually going to set a timer. Yeah, I'm going to set a timer on my phone just so I don't forget. I'm going to set a 25-minute timer And then after that, we're going to start talking about the next one. So can I get you guys to start working on 10.4? If you've got any questions, let me know. But I'm going to leave you guys to it. And I'm going to quickly, I'm going to spend some of this time helping you guys out if you get any problems. What is an idealization? I can look that up. It's actually something, it's actually written. It's actually written here in that one that I was just looking at before. Idealizations. So you guys can look that up. But I'm going to give you guys, or you can read that part of the text and find out what it means. I'm going to give you guys 25 minutes. If you've got any questions, let me know. And I will answer them to the best I can. But I'm going to quickly read this section here so that I can explain it to you and not get it wrong. Because I was about to explain it and I was about to get it wrong. So 25 minutes, 10.4. 10.4 go. What's the difference between question 2A and 2B? Someone asks. Also, someone then asks, how much time have we got left? Let me have a look, shall we? Firstly, I'm going to check that I'm not having muted myself, which is very, very likely. How do I check? Oh, no, I'm not muted. Cool. You guys can hear me. Hey. Okay. So, firstly, there's about, I think there's still a lot of time left. So it's about 17 minutes left. Okay. So 2A and 2B. The two, when a spaceship takes off at its initial acceleration is 3 meters per second squared and its initial mass was about 2.2 times 10 to the power of 6. Determine the magnitude of the net force of the spaceship as it takes off. Determine the magnitude of the upward thrust as it takes off. Okay. From first inspections, it looks like it's the same type of question, but I think it might be different. So I think the first one is like, well, you've got this acceleration, you've got this force. And I think the second one is, what is the magnitude of the upward thrust? So notice how it's not talking about the force, it's talking about the upward thrust. So I think what you'll find is that to do the second one, you need to recognize that a rocket has, oh man, that's a great rocket, Mr. Greer. Look at that. Cheating. So a rocket is going to have a force upwards. Oh my God, I'm going to keep cheating because I can. It's going to have a force upwards, like that, and it's going to have a force downwards. Now we know what the net force is, right? The net, you can also just base these off accelerations. But we'll do the net force. We know the net force is upwards. And that's going to be whatever this and this. So it's going to be, we're going to call that 6.6 equals 6.6 times 10 to the 6 newtons. But that net force has to be made up of two forces. The force of gravity downwards and the force of the thrust upwards. So what you need to do is you need to use the fact that you know that that force is going to be 9.8 times 2.2 times 10 to the 6. And if you know what that is, and you know what that is, you can work out what your thrust, your upwards force must be. I think that's what the question is asking you to do. As I said, I haven't checked the answers yet, so I don't know if that's what you need to do, but that's how I would tackle question 2B. It's trying to get you to practice these net force diagrams understanding. Oh, someone asking another question. What's this? Are we doing the whole 10.4? Let me have a look. Let me have a look. And I'll decide. Question 1 and 2, yeah, sure. Question 3, yep. Question 4. Oh man, question 8 is hard. Oh, it's not too bad. Why don't okay, Roshan, you do everything except question 8. I might do question 8 with you guys quickly at the very end. Well, I might do question 8 with you guys at the end of your working time, which is in about 12 minutes. Uh, About 3 minutes left, ladies and gents. And then we're gonna keep going through. I've been fixing some slides as we've been going, just so that we can, yeah. Oh, shit. Scared the living. All right, guys. Hey, this is the end of the working time. What I'm going to do with you guys now, so I'm actually going to tackle. You guys are still here. I'm going to go back up because I was scrolling around looking at some of the stuff for Newton's third law. What I thought I might do is I might go through question 8 with you guys, just because it kind of gives an interesting point. You guys can copy this down if you want, or you can just watch me do it, and then when you come to do it, maybe you remember it, maybe you want to take some notes. Up to you guys. I still want you to do it though, but yeah, I thought I would do it with you guys quickly here. And I think it might be a bit useful for us to talk about anyway, because it's one of the ones that I sort of ignore with Newton's second law. With Newton's second law, we've got to take into account the fact that what we're going to take into account is that it deals with net force. Okay, it can deal with any force, but usually what we use it for is to deal with net force. So when we talk about net force, we're gonna have to talk about how are the other forces at play. I'm going to show you guys this here. Okay, question 8. A physics teacher decides just for fun to stand on some bathroom scales calibrated newtons in a lift. The scale provides a measurement of the force of which they push up on the teacher. When the lift is stationary, the bathroom scale reads 700 newtons. What is the reading of the scale when there are different circumstances? So before I even start that, I want to quickly draw this here. So we've got a lift. we've got a physics teacher. In this case, it's me because surprise. And they're standing alone. Initially, the force that the scale reads is 700 newtons. Now that's force is 700 newtons. That means that there is a force downwards, and that force downwards is gravity. So this is the gravitational force of 700 newtons. Now because we know that Fg equals m times g, we know that 700 equals mass times 9.8. That means that our mass of our physics teacher is 700 divided by 9.8, which is 71.4 kilos. Man, I wish I weighed 71.4 kilos. I do not. So the question, though, is that's not the question. We haven't even started the question. The question says, the lift is, what will the reading of the scales be when the lift is moving upwards at a constant speed of 2 meters per second? So a lift is moving up at a constant 2 meters per second. We'd say, well, is there any acceleration? If this is a constant acceleration, so F net equals 0. There's no acceleration, so therefore the F net equals 0. So therefore the reading is going to say for A 700 newtons. Okay, that's what it's going to say is 700 newtons, because that's how much, because there's no acceleration. Okay, that was a trick question, so be careful for that one there. There's no acceleration and there's no forces at play. For B, though, they changed the game. Now it's accelerating downwards at 2 meters per second squared. So now, pardon me, it's going down at 2, sorry, I should use a different color. It's now going down at 2 meters per second squared. So now there is a net force. Okay, so that means we've got so if we've got a net force, let's look at all of the forces that are going on here. We've got a force downwards, which is going to be caused by gravity, and then we've got an additional force downwards, which is going to be caused by the lift moving down. So I should have used green. And so therefore F net is going to be the force of gravity plus this force downwards. Now we already know what F and G is, because Fg we've already calculated 700 newtons. So this force downwards, though, that's going to be, well, we know the force, we know the acceleration, Fd, is going to be the mass times the acceleration. We know that the mass, we already calculated the mass was 71.4. And we know the acceleration downwards, well, that's 2. So that's going to be 71.4 times 2. It's 143 newtons. So that means we're going to add 143 newtons. So that means our force, our net force downwards is going to be 843 newtons. And that is a bigger number. And that's why you have a, and that number is going to be, you're going to experience a different force if you're going downwards, where if the force is going downwards. Hold on. Shit. I got the question wrong. I hate when that happens, because that's not what the force is going to read. Because even though How do I explain this? My problem that I have with this is that I know that this is the wrong answer, but I can't tell you very well why I know this is the wrong answer, because sometimes not the greatest physics teacher. I haven't taught this before, so that's why. I can tell you this is the wrong answer because I know that when you're in an elevator, from personal experience, when it goes down, you don't feel heavier, you don't feel more force, you feel less force. Kind of feel like you're floating, which means that these two numbers shouldn't be added, they should be subtracted. I think the reason that they should be subtracted is because even though the gravitational force is downwards, it's actually measuring, the force that it's measuring is the amount that you're pushing down on it. So therefore it's more upwards. So I think this should be a negative here. As I said, I'll have to check the answers. I can't believe we've stuffed this question up so badly. I apologize, but I'm pretty sure the answer should be 557 newtons. Whereas when you're moving upwards, the ground is getting forced into your feet. So for question 8, this is what happens when you try and impress the students. Question C is the last one. That's when the elevator is moving upwards of 2 meters per second squared. That means that it's going to be, the two forces are going to be in line. So therefore Fg plus F up is going to be, and it's going to work out the same way. You're going to end up with 843 newtons. Saying that though, I probably stuffed that up, but I'm gonna have to go back. I'll go back over this. I'll make you a deal. I'll redo something like this next lesson when I talk to you guys, and I'll refix up and figure out where I made a mistake. But hopefully this gives you guys a bit of an idea of how to tackle question 8. So now what I'm going to do is I'm going to jump back over to here, and I might not get time to do all of Newton's second law, third law, but I will start to talk about it. I'm going to add some questions here, some free body questions, just so that I guess for me, my benefit, next time I teach this, that I've got them in here. But for you guys, if you guys want to look at these later on, then maybe I can go through them if you want. What I wanted to talk to you guys about, though, before I moved on, was this guy here. Now, this is what I was going to explain to you guys before, but I was really concerned that I was going to stuff this up. So that's why I've decided to read up. In that 25 minutes, I decided to read up to make sure that I got this correct. So falling through the air. This is one of the classic physics examples. And what it is if you had a bowling ball and a feather and you drop them in a vacuum, both of them will have an acceleration of 9.8 meters per second squared. Now, what does that mean? That means that for every meter per second, for every second, it will fall 9.8 meters. Its speed will increase by 9.8 meters per second. So after 1 second, both of them will be traveling towards the ground at 10 meters per second. This doesn't matter. It doesn't care about the weight of the object. It doesn't care if it's a heavy bowling ball or if it's a light feather. They will both fall at 9.8 meters per second squared towards the ground. And they'll both reach the ground at the same time. And that's really counterintuitive, especially because I know a lot of you guys have dropped feathers and you've dropped bowling balls. And hopefully by now you guys know that the reason that this doesn't work is because of air resistance. Normally we would ignore air resistance, but in this situation you can see why air resistance is such a big deal. Air resistance changes a lot about the forces going on here. one of my problems that I have is I've tried to teach this to year 7 students, and it's really difficult to teach this topic because they always, it's hard to explain that they're supposed to be falling at the same speed, but they're not, and why. So the example that we usually give students to work through this is we get them to cut out 2 pieces of paper. One they turn into a disc and one they crumple up into a ball. But the idea is that they're both the same mass. So therefore, they're the same mass. They should both hit the ground at the same time, but they don't. And the reason that they don't hit the ground at the same time is because because the scrunched up paper is lighter. It has a because the scrunched up paper has less surface area, it's got lower air resistance, so therefore it hits the ground, whereas the lighter one floats down. And so you say, well, if they were both the same mass, then surely they should hit the ground at the same time, right? But they don't. So this like air resistance is important. So if we had no air resistance, they would still hit the ground at the same time. And it actually wouldn't matter how big a piece of paper you used. Now, the formula, so it says, yeah, so someone asked, will they fall at the same time on the moon, considering the moon has no air? And yes, they do fall at the same time on the moon. One of the classic, one of the very first experiments that they did when they reached the moon is they dropped a feather and a hammer. So they actually took a feather to the moon for this purpose, which I find a bit amusing. And they dropped them and they recorded the speed that they took to hit the ground. You can watch the video of it, like there is an Apollo mission of them doing it, but it's very, very, like, because it's 1960s, it's very blurry and hard to see. But yeah, essentially they hit the ground at the same time because there's no air, so no air resistance. So I wanted to explore this formula here. So down the bottom, the net force, the acceleration, so the gravitational acceleration of experience is going to be caused by the net force downwards divided by the mass. Now, the problem is on Earth is that you haven't just got the force by gravity pulling it downwards. You've also got this idea here. You've got this air resistance. And that air resistance is going to remove from the force of gravity. It's going to be another force acting. So what does this look like? Well, you're going to have, and the reason why it's negative is because you will have, let's just say you got your feather, yeah? This is a feather. Trust me. That's like an amazing feather. So you're going to have a force upwards, which is going to be your force of air resistance, and your force downwards, which is going to be your force of gravity. And you need to add both of those together to get your net force. So remember, your net force is your addition of all of the forces. So if you add your force by air resistance and your force of gravity, which is going to be minus because it's in the opposite direction, you get your net force. And that divided by the mass will give you acceleration. In comparison, the bowling ball, right, is still going to have air resistance, right? But the problem is that the difference, the problem is that for the bowling ball, this force downwards is going to, let me see if I can just, this force, where is it? Yeah. This force downwards is going to be massive compared to the air resistance. So therefore the air resistance is not going to do very much. It's going to really not change this formula very much. So that's why we usually ignore it, because most of the time the force by gravity far outweighs the air resistance. But in this case, it doesn't actually apply. But yeah, I thought this was important to go through, especially because a couple of questions asked about it. Plus, it's another chance for us to use this idea of the net force, even though I just stuffed it up going through a question just then. But yeah, that's how you would do it. Now I've got about 10 minutes left. I'm going to save the last 5 minutes to show you guys. So what I'm going to do with the last 4 minutes, and you guys can leave at the last, so you guys can leave a little bit early if you want. The last 4 minutes I'm going to put on a YouTube video that I've just attached to the one of my classroom, and it is literally what they did. They did this experiment. Brian Cox, famous physicist, actually did it, and he actually put it in the world's largest vacuum, like the world's largest vacuum chamber, and recorded it. And like, he did it just for the sake of, people don't think that this happens. People think, oh, lighter things will fall slower, but it's not. The only reason lighter things fall slower is because they're forced by gravity is close to the air resistance force. So let's start talking about Newton's third law. I'm going to break Newton's third law into 2 parts. Today's lesson, and on Thursday's lesson, we're going to talk about how Newton's third law affects motion. So we're going to start with Newton's third law right here. Now, there are different ways to refer to Newton's third law, just like there are different ways to refer to Newton's first law. But I prefer, but this is the proper way, or at least one of the proper ways. So what is it? Whenever one object exerts a force on a second object, the second exerts an equal force in the opposite direction on the first. Now, if you're not a native English speaker, this probably is like, what the hell is going on here? And so I usually summarize it as this. For every action, there is an equal and opposite reaction. So let that sink in for a second. What this means is that if you do an action, you apply a force to something, let's just say you push against the wall. The object, the other object, the wall, will exert the same force. It'll push back on you the same amount that you push on the wall. And it will do this in the opposite direction. So if you push towards the wall will push back on you. That's why whenever you touch a wall, your hand doesn't go straight through the wall, because the wall is applying the same force backwards. It's counteracting your force. Now, Newton's third law is, in my opinion, the hardest. And the reason I think it's the hardest is the first law to now bring a new idea into the mix. What idea the third law brings in is this bringing more than one object. Think about the first law. An object in motion will stay in motion. Object at rest will stay at rest. That's just one object, right? Don't care. For the second one, if that object experiences an acceleration, it experiences a net force, it'll speed up. That's again one object. Now we're dealing with 2 or more. When one object exerts a force on a second object, we're dealing with 2 objects. And of course, if you start getting more complex, this object's applying this force this way, but this force this way, you're going to start having a lot of forces going on. So this is what makes this a little bit more complicated. Let's look at our very first example of Newton's third law, which is this guy here. My classic example is the magnet and the paperclip. Now, straight away, can you guys tell me what's going to happen in this scenario? What's going to be the thing that goes on? If I bring a magnet near a paperclip, what's going to happen? Easy answer. Someone in chat
Attract.
or out loud. What's going to happen if I bring a magnet to a paperclip?
Attract.
Oh crap! I've muted it. No, I haven't. Attraction? I may have muted it. Sorry. Sorry about that, Kelvin.
That's all good, sir. Yeah.
So they're going to be attracted. So the The paper clip is going to be attracted with some force towards the magnet. But because of Newton's third law, that means the magnet is going to be attracted to the paper clip with the same force. These forces are the same. They are on different objects because the magnet pulls the paperclip and the paperclip in turn pulls the magnet. They're the same force, but they're in opposite directions and they're on different objects. And so this brings up the Newton's third law. If you pull on a paperclip, the paperclip will pull on you. If it was repelling, if two magnets repel, one magnet would push on the other magnet would push back. So a great way to tell whether or not a situation, whether or not you want to take notes on this is up to you as well. How we can go about breaking this down is I usually refer to, and this is how they refer to in the textbook, as action-reaction pairs. Newton's third law can also be stated that all forces come in pairs. So just like how the magnet and the paperclip had these two are action-reaction pairs. If this is the action, then this is the reaction. The two forces are action-reaction pairs. They must be the same size. They must act in opposite directions. And this one here is probably the clencher. They must act on different objects. And I think I might use my last 5 minutes to explain the importance of that one. And then I'm probably going to maybe go through the rest of Newton's third law next time. But I'll talk about that one here. What do I mean by different objects? This is the classic example that I usually give. I'm going to draw it down the bottom here. So what I'm going to do is I'm going to draw a hold on a second. Believe it or not, it's actually very difficult to draw a straight line. That'll do. So the classic example that usually gets given to this is, imagine you've got an apple sitting on a table. Well, I don't know if it's a classic example, but this is how I normally teach it. Now that apple is going to experience two forces. It's going to experience a force of gravity that's going to pull it down. That's supposed to be down, but obviously not quite. We call that FG. I'm going to maybe switch this to black so you guys can actually see that it's an F and a G. But it's also going to experience a force upwards. The force upwards it experiences is going to be the normal force. The normal force is pushing it upwards away from the table. And what you would then do is you'd say, well, are these action-reaction pairs? Well, let's check. And of course, one more thing. So I'm going to say the net force is 0. So there's no net force. All the forces are balanced. So let's check this. Are these in the same size? Well, they must be the same size because the net force on this apple is 0, which means that apple is at rest, or it won't, or at least is moving at a constant speed. Are these acting in the opposite directions? Yes, they are. One is going down and one is going up. So therefore, they are acting in opposite directions. Are these acting on different objects? Well, one's acting on the apple and the other one is acting on the apple. So no. And this is why this one is so important. They're not acting on different objects. So in fact, these are not action-reaction pairs. If the table experiences a If the apple experiences a normal force of the table pushing it up, then the apple must be pushing the table down with some kind of normal force. Okay, and if the gravity is pulling the apple, if the Earth's pulling the apple down by gravity, then the Earth must also be being pulled up by the apple. Those are the action-reaction pairs of each of those, because they're acting on different objects. But a lot of students get that wrong and they get confused. That's why I usually, whenever I get a student say, is this action-reaction pairs? I go, well, let's check it. Are they the same size? Yes. Are they in the opposite directions? Yes. Are they on different objects? No. Well, then they're not action-reaction pairs. Let's grab a look at these ones on the left, on the right here. So the first one, we've got a girl standing on, exerts a force on the ground because she's pushing down the ground because of gravity. Hence that normal force is the apple pushing down because of gravity forces it to push down. So the force the girl exerts on the floor, and then there is also the force that exerts, that's gravity pushing down on the floor, but the floor also pushes up on the girl. That is the normal force. So that's what's going on here. Same situation as this apple. Let's grab a look at the soccer ball. The force that the foot exerts on the ball, so the foot pushes the ball up to the right, and then of course you can see here, the force the ball exerts on the foot. The ball exerts a force on the foot in the opposite direction. It's the same size, but it's in the opposite direction. The force the bus exerts on the car is backwards, but the car exerts a force on the bus forward. I've been in a car accident before. A guy crashed into me, like rear-ended me. I'm actually going to talk about that accident probably again, but yeah, I looked at his car and my car where there was damage on both cars. It wasn't just like he crashed into me, so the damage was on my car. We both put a force on each other's cars. So we both damaged. So in the end, the bus will get damaged because it experiences a force, and then the car will get damaged because it will experience a force. How much it gets damaged depends on the type of car and how it's built and the acceleration that car experiences. Last one, and this is perhaps one of the hardest ones to do, but I've already just talked about it. The Earth pulls down on the brick with the force of gravity, but the brick pulls up with the Earth with the force of gravity. That one's really hard for people to understand because they're like, what do you mean the Earth gets pulled up? Because you don't see it. The Earth is so large, you don't see the force acting. But there is a force acting. The Earth does get pulled up by a small amount of force. Right, I'm not going to cover the rest of this stuff, but that's an introduction to Newton's third law.